In this video, we're going to talk about approximation. When you go to the lab and you grab a voltage source of 10 volts, we make the assumption that's really a 10-volt source. Or when we grab a wire, we go, oh, this wire has a zero resistance. That's not true. So let's talk about the first approximation, which is the ideal approximation. So when you take a wire that's 1 inch long, in the lab we go, don't worry about it, that has a value of R equals to 0. That's not really true there. A 1 inch wire here would have an inductance roughly of 0.24 microhenry and a capacitance value of 3.3 picofarad. It's going to behave like an inductor and a capacitor. With a low frequency, these numbers are no big deal. But as the frequency increases, that becomes a problem. The reason for that is the inductor actually has a value is known as equal to j omega L. And the capacitor is going to have a value of 1 over j omega c, or a lot of times you write that negative j over omega c. So if the frequency we're using, let's say it's 10 mega. So let's assume our frequency here is actually 10 megahertz. That means W is going to equal to 2 pi f, which is 2 pi times 10 megahertz. Let's do the math for that. What's W is equal to? Where's my calculator here? W is going to be 2 times pi times 10 EE, where's EXP, where is it, that EE here? Oh, right here. 10 times 2 times pi times 10 to the power of 6. That's what a mega is. So let's see what the frequency is, or W, not the frequency, W. So W in this case will be 62831.853 roughly. So that 1 inch wire now will have an inductance value equals to J times 62831.853 times the value of that inductance, which is 0.24 micro, so multiply that by 0.24 EE to the negative 6, and it's going to have a value of roughly 15J. And it's going to have a capacitance value equals negative J over omega C. So that's going to be negative J divided by omega, which is 62831.853 times C, which is what? 3.3 picofarad. We do the math. Let's see. 62831.853 times 3.3 EE to the negative 9. And we do 1 over that. And that will have a value of negative 4.8 J ohms. So notice at 10 megahertz, I use 10 megahertz here. Yep. At 10 megahertz, we have a large value there. That capacitor, or that little wire there, it's no longer just that little tiny value. We have a 15 J ohms inductance value. We have a negative 5 roughly J ohm capacitance value. So imagine if we're working next to a radio station. That's what happens to us here on campus. Our radio station right next to us. Our frequency is 90 megahertz. So you put in 90 megahertz here, these numbers even magnified much larger. So we can't really neglect the resistance of these wires or the impedance, the capacitance of these wires. As long as your frequency is below 1 megahertz, you're going to be okay. You'll be in the neighborhood. So the rule of thumb is, as long as the frequency is below 1 megahertz, you can pretend the wire is actually a short circuit. But if that frequency is really below 1 megahertz, then we have a problem, because this number actually, once you go to 1 megahertz, becomes 1.5. Not that big of a deal. And this number will change, will become a little bit smaller too. So as long as the frequency is under 1 megahertz, you can replace the wire with a short circuit, but if it goes beyond that, we really need to include this in our calculation. We can't just neglect it. That's what we call the first approximation, ideal approximation. Now the second approximation we make, let me just put that paper aside. Second approximation Now, this approximation, like when you have, for example, you're building a circuit, and this circuit requires, I don't know, a 9-volt battery. So you go and you get your 9-volt battery. There we go. And you attach that. That's the 9-volt battery. The assumption made here that this battery has no internal resistance. So you're only getting 9-volt battery, but there is no R. Again, the reality of this, there's actually roughly, there's approximately, that's approximately 1 ohm resistor in series with the source. So that 9 volt is not really 9 volts. Let's give you an example here. Here's your 9-volt battery source. The assumption made here, there is no resistor here. There's 0 value. So if there's 0 value, there's your load here. We'll call that R sub L. Make sure it's adjustable. And you go, well, R sub L in parallel with this. If this is 9 volts here, then the voltage cross R sub L is going to be 9 volts. But what about if this value is really small, the value of the resistor? Let's see. Here's the 9-volt battery that you took. Let's say this actually battery has a resistor on the inside of 1 ohm. But now this resistor here, it's only 4 ohm resistor. So what is the value of that? So the voltage here equals 9, voltage division, times 4 divided by the sum of them, which is 4 plus 1, and that will give me what? The voltage is 9 times 4 divided by 5. And notice we are not getting 9-volt battery here. 9 times 4, let me just turn on, 9 times 4 divided by 5. We are getting 7.2 volts. So we didn't get actually the 9 volts we're supposed to get. The assumption there's nothing here, I should get 9 volts regardless what I put here. The reality is not the same. The lower this number, the less voltage you're going to have here. So how do we deal with that? What are the rules we should use? When do we count this? When we ignore it? Well, for that you have to go to the next video.